All right, so far in this section, we've been dealing with areas between curves. We did a few examples in the last video. And now what we want to do is look at an application of this concept. So there's a little bit of setup for this. There's a little bit of kind of prerequisite understanding of economics, specifically supply and demand. So I'm going to assume that you have some familiarity with that. Because we can't launch into a full economics style lecture on that. So if these are unfamiliar topics to you, you're going to want to brush up somewhere. You can Google some of these terms and learn a little bit more. But I think even people who have not had a course in economics are familiar with the terms supply and demand. So basically, very briefly, when you are dealing with a particular product that somebody is producing and selling, we have what's called a market price for that product. It's kind of a determination of what the pricing should be for that product. And that market price is influenced by a couple of factors. One, it's influenced by supply, which in other words is just the availability of the product. How much is there available and ready to be sold? Then it's also that market price is affected by demand, which is consumer desire for that product. Is that product in demand, or are people not really wanting it? Both of those things determine the pricing of a product. So in addition to that, both of those factors, both supply and demand, are usually modeled as a function of X, where X is what we have been calling it for a lot of these application problems. It's the number of units of product that are available to be sold. So they have been produced and are ready to be sold. Okay. The more products that you have produced, the greater your supply. So you can see directly that supply does depend on X. And we know from economic theory that supply affects demand. Those two things are related. So in turn, that means demand is also related to X. So each of those can be thought of as a function of X. And we use this notation for it. The supply function, which again depends on X, we call S of X. And D of X represents your demand function. And in both of these cases, pricing is set according to values output by these functions. And so if we let P be P represent price per unit of this product, and we think of it as kind of a dependent variable with X as an independent variable, then we have functions which can in turn be graphed. And this one, P equals S of X, we call a price supply curve. P equals D of X, we call a price demand curve. Okay. Now, what typically happens, and again, this is from economic theory, so if you want to know the details of why this happens, you need to go, take an economics class or read up on economics. We're not going to get into all of that here. But these two concepts, the supply and demand, are inversely related to each other. So what that means is that if demand is high, then generally supply will be low. If supply is low, then demand will be high. And there's a lot of other factors that complicate that concept, but that's at the most basic level. That's kind of how we can think about it. So what that means in terms of these functions, if we were to graph them, is that generally one of those curves will be increasing, whereas the other one will be decreasing. And because of that, they will tend to intersect at some point. So if we graphed both of these functions on the same set of coordinate axes, we would see a point of intersection between those two. And that point of intersection is what we call the market equilibrium point. The price, which remember, that's like the dependent variable, so we would think of that as the second coordinate. The price at that equilibrium point is called the equilibrium price. And if you think about it, it's where this P is equal to that P. It's where the price determined by supply is equal to the price determined by demand, and that is the ideal market price for your product. That's how we determine what market price is. Okay? Now, that is just the setup for the concept that we're talking about. This is all stuff you would talk about in an economics class. We want to use that concept to describe something called consumer's surplus. So here's how that works. In most markets, you get consumers who are willing to pay more than the equilibrium price for a product. Now remember, equilibrium price in an ideal circumstance is what sets that market price. So, if you have a particular product that, let's say, is being priced at $5 per unit, you may have people who, you'll most likely have consumers in that market who are willing to pay greater than that amount. Maybe somebody's like, I'm willing to pay $9 per unit for this thing. So if that's the case, if they only have to pay that equilibrium price, which is what the market price is generally going to be, then they're going to assume that they're saving money, because in their minds, they would have been willing to pay more, but they're only having to pay $5. So because of that, the consumer is interpreting that market price as almost like a discount, and they're saving money off of that. The total amount of savings for all of these consumers who are willing to think of this in these terms is called consumer's surplus. And what we want to do is find a way to compute for a given product with a given price supply curve, given price demand curve, which, with an equilibrium price that will be determined by those things. We want to find a way to compute consumer's surplus for that market, for that product. Okay. So I'm going to use this graph to kind of illustrate some of these points. And this graph shows us a little bit more than we're talking about right now. We're going to get to this producer surplus thing in a little while. But here is an example of those two curves that I was talking about. So we've got these two axes. The x-axis, remember, x represents the number of the amount of products that have been produced, or number of units of that product is a better way to say that. That is oftentimes called quantity in these graphs. P was what we thought of as our vertical axis, which is the price, or the pricing per unit for our product. And we have these two curves here. We have this red curve, and then we have this blue curve. Notice the red curve is the demand curve, and the blue curve is the supply curve. So when supply is very low, demand is high. But as supply increases, demand will decrease. A lot of the times in an economics class, these are represented as lines, but they can be curves. Notice, because one is decreasing, the other is increasing, they have to intersect somewhere. And that intersection is what we were calling equilibrium. The price at equilibrium is market price. So this market price, it's not a label for this axis. It's specifically talking about the price at that equilibrium point. The x value of that point is the equilibrium quantity. It's the amount of product that needs to be produced and ready to be sold to take us to that equilibrium point. Now, what we were talking about was consumer surplus. So notice where consumer surplus is. We're going to make an argument for this, but we're going to show that consumer surplus is basically always going to be the area of this region, where this region is defined to be the region below your demand curve, but above equilibrium. So above the equilibrium price. And notice that would be a horizontal line going through your equilibrium point. So we can think of this as P equals P naught. That would be the equation for that. Okay, so to make an argument for why this is consumer surplus, I'm going to go back up here. So again, remember, we're thinking of consumer surplus as savings, right? The consumer interprets the equilibrium price, if they're willing to pay more, as almost like a discounted price, and so they are saving money. How much are they saving though? Well, the demand is kind of what determines what people are willing to pay. If demand is high, people are generally willing to pay more money for a product because it's hard to get a hold of, and it's they desire it more. So if the demand for a particular product is determined by D, and we have a specific quantity that we're plugging into that. So a specific X value down here, let's call it XI. Then D of XI determines the demand, which is kind of like the maximum amount people are willing to pay per unit for this product. If we subtract the equilibrium price from that, that's basically telling us how much they think they are saving by paying the market price. Now, what we're going to do is say that this is all for a particular value of XI. And we can approximate that by a little subinterval. So if xi is down here, I can put a subinterval around that, which has a width of delta x. And the reason that's there is because we need to consider the number of units that somebody is buying, right? This d of xi minus p naught, that's the amount of savings per unit. But then if you want to compute a total number of savings, you have to multiply that by the number of units somebody is purchasing. Number of units can vary, and so we use a little subinterval to kind of approximate that. If the width of that subinterval is delta x, then we would do the savings per unit times the number of units to determine the total savings. Now that is just for a little subinterval surrounding that point xi, that should be an I. But there are various different quantities that we have to consider from 0 all the way up to this equilibrium quantity right here. And so instead of just considering this one level of quantity, we want to do this for a bunch of subintervals that we can approximate here. Okay, so if we compute this consumer surplus for all of these different subintervals and then add them up, we're getting the total amount of consumer surplus. Now remember, that's actually just an approximation because that little subinterval that I put around xi is kind of approximating what's going on at that particular quantity, right? But that approximation is better if that subinterval is smaller. And so to make these subintervals smaller and smaller, I need to partition this interval up into more and more of them, which means I need to increase this n right here, which represents the number of subintervals, indefinitely. In other words, we want to take a limit as that n goes to infinity, which takes this thing, which is a Riemann sum, and turns it into an integral, this integral specifically. And this, based on all of that derivation, is how we compute consumer surplus. So consumer surplus is the integral from 0 to x naught of d of x minus p naught dx. And as a reminder, the equilibrium point is the point x naught p naught. This is where that x naught and that p naught are coming from. So again, p naught is market price, x naught is equilibrium price, or equilibrium quantity. Okay, that's, yeah. So, and now that we have defined it that way, remember throughout this section we have been talking about areas between curves. So this is a difference between two functions, which in the d of x is the higher function between these two. P equals p naught would be this horizontal line. So this represents the area between these two curves, which is why this is labeled as consumer surplus. Okay, hopefully all of that made sense. So now at this point, we're going to look at an example where we need to compute consumer surplus. We're going to use the same price demand function for this, but we're going to do this in 3 parts. So for the first part, let's read it. The price demand equation for a certain market is P equals 600 minus x squared over 294, which gives the price per unit when x units are demanded. We want to find the consumer surplus in all 3 of these situations. So remember, the price demand function, we usually use P equals D of X for that. This is the D of X right here. Notice it's P equals this function of X. So in the formula for how to compute consumer surplus, that's what we're using as our D of X. All right, so for part A, we're given an equilibrium point, which means we have an X naught and we have a P naught. So the formula for consumer surplus says I take the integral always starting from 0 up to that value of X naught, 294, of D of X, so that's 600 minus X squared over 294, minus P naught. P naught is 306 dx. Combine the constants, so this is going to give me the integral from 0 to 294 600 minus 306 is just equal to 294. Like that. Okay. Integrate this. This is going to become 294x minus x cubed. Remember, I'm multiplying this by 1/3, which is like multiplying that 294 down there by a 3. That's 882. And we evaluate from 0 to 294. Okay, this, I plug the 294 in. 294 times 294 is just 294 squared minus 294 cubed over 882. And then I can see that if I subtract 0 after, or this function with a 0 in it, all of these terms go to 0. So I'm just subtracting 0 there. This comes out to $57,624. Remember, we have to interpret that as dollars because this is what the consumer is interpreting as their savings, total savings, okay? So this is consumer surplus is always interpreted as a dollar amount. That's our consumer surplus for this first example. Part B, the equilibrium quantity, remember that's X naught, is 120 units. In order to compute consumer surplus, we need both X naught and P naught. It's only telling me X naught. However, X and P are related by this function. So if I want P naught, I plug X naught into this function. So P naught is equal to 600 minus, we said X naught was 120, so 120 squared over 294. Now, this comes out to a decimal, and I have said before that most of the time we don't want to deal with decimals and rounding unless it's an application problem. And this is an application problem. So it's one of those cases where you do want to deal with decimal. Specifically, because we're representing this as a price, or we're thinking of this as a price, round it to 2 decimal places because that's what would look like dollars and cents. So this, you can just go into a calculator. After rounding, you get this amount, $551.02. So $551.02. Okay, we can now set up our integral. So this is the integral from 0 to 120 this time, because that is what the X naught, or the equilibrium quantity, was. Setup will look similar, 600 minus x squared over 294, but this time I'm subtracting not 306, but this equilibrium price, or this market price, 551.02 dx. Simplify, so do 600 minus this, that should be a 1, sorry. Subtract these constants, and we end up with 48.98 minus x squared over 294 dx, okay? This is now going to feel very similar to what we did up here. We just have a different constant and a different upper limit of integration. We're going to get 48.98x minus x cubed over 882. That term looks the exact same as before, this time from 0 to 120. Okay? This is equal to 48.98 times 120 minus 120 cubed over 882 minus, when I plug a 0 in, everything goes to 0. This, again, you're going to need to round, but it's fine because it's not an application problem. This represents dollars and cents. We get 363.73. Okay, that's consumer surplus for this one. Let's do one more part, C. This one, it's the other, we're given the other information. We're told equilibrium price. We are not told equilibrium quantity. So again, if I know P naught, I have to use it to find X naught. Okay, so I'm going to set this P equal to 150 and then solve the resulting equation for X. That's going to look like 150 equals 600 minus x squared over 294. Subtract 600 from both sides. I'm going to get negative 450 equals negative x squared over 294. This is going to give me x squared equals, I'm just going to multiply both sides by negative 294, which gives me 294 times 450. I didn't compute that because you don't really need to. X squared, to solve for that, I would just get x. I would take square roots. And this is I have to round it, but it comes out to approximately 363.73. Careful with this, because normally when you take square roots of both sides of an equation, you're supposed to get a plus or minus on one side. However, x represents the number of units of product that have been produced. A negative answer would make no sense here. So even though this should produce two solutions, only one of those solutions makes sense in context, and so we go with that one, 363.73. Now, this becomes my upper limit of integration, 363.73, and we can set up our integral. So demand function, 600 minus x squared over 294, minus my equilibrium price. That's the thing that was given to me in the beginning, 150. Dx, this is going to give me this, 0 to 363.73. Subtracting will give me 450 minus x squared over 294. All right, now since I have done these types of integrals so many times up until this point, I'm not going to go through the work. I'm going to do this. There are some steps that I'm leaving out. That's what the ... means there, but they are so similar to what we've already done, I'm going to let you do them. What this comes out to is approximately $3,840 for your consumer surplus. Okay? We're going to end this video here, and then we're going to do one more topic on producer's surplus, which we saw in that graph with another example similar to this one in part 3.